Hi, hello friends. Welcome back to my channel. In this video, we are going to continue the concept of few concepts, important concepts from current electricity, which will be useful for Hstr exams, Gpstr, and also for CET and Central TET exams also. Okay. Already we saw a few basic points from this electricity chapter, current electricity. Kindly go to the description box of our video and you can check out the link of that videos. Okay. Already we have taken enough maths classes related to Gpstr exams also. If you go to the playlist, maths playlist, you will get all these videos which will be useful for Hstr exams also. In the following classes, we shall continue to analyze the question paper, previous year question paper of Gpstr and Hstr also. Okay. Before moving to the video, if you are new to the channel, kindly do subscribe and press the bell icon so that you will get the notifications of all the videos we upload here. Okay, so in this video we shall check out with potential difference, drift velocity, relation between current and drift velocity, and mobility of free electron. Very important points for the exam point of view. Let us check it out now. Potential. What is potential? The amount of work done in bringing a unit positive charge from infinity to that point is called as potential. So imagine there is a test charge at infinite distance. So here is the positively charged particle, let us take. Here there is a positive charge particle and at infinite distance, ಸ್ವಲ್ಪ ದೂರದಲ್ಲಿ ಅಂದರೆ ತುಂಬಾ ದೂರದಲ್ಲಿ infinite distance ಅಲ್ಲಿ there is a positive charge, let us take, consider. So if we need to bring this positive charge from infinity to this point, some work has to be done. Okay, because here both are like charges, positive and positive, and they will try to repel each other. So against this repulsive force, there must be some work done in bringing this positive test charge from infinity to this point. So some work you are doing in bringing this charge. Okay, so that is called as potential. So V is equal to W by Q. Suppose here there is a positive charge particle, and here there is a negative charge. How do we bring this? While bringing, both are like unlike charges. This is positive and negative. Unlike charges, they will attract each other. While attracting also, they will have involved, some work is involved here. Okay, they will perform, the work done is done by the attractive force this time now. Okay, some work is done by the attractive force along with this charge. Okay, so this is called as potential, and we can write potential is V is equal to W by Q, and SI unit of potential is volt. So this is by the name of a scientist. Okay, names Alessandro Volta. Okay, he was the one who gave this definition, and so his name only is kept. And when we write this SI unit by full word, all the letters should be of small letters. Okay, only when we write the symbols with the name of a scientist, it should be capital letter. Otherwise everything should be small letter, even though it is under the name of a scientist. And 1 volt is also can be written as, what is the SI unit of work? It is joule. So joule, for charge it is coulomb. So joule per coulomb is also the unit of volt. So you can write 1 volt is equal to 1 joule per coulomb. And potential is a scalar quantity. Okay, it deals with only the magnitude. Okay, it doesn't say anything about the direction. Hence, potential is a scalar quantity. Next, before moving to the point potential difference, let us recall few points related to potential difference. So here, imagine that there are two vessels, vessel A and vessel B, and irrespective of their shape and size, it could be of different shapes and different sizes also. Okay, and it is filled with water, let us imagine, and they are connected, joined together. And now the water level at A has high, and it is having high pressure, and here this is having low pressure, water at B, and hence the flow is due to the difference in the hydrostatic pressure, we call it is. So because of the level of the water in the two vessels, and water from A to B flows till both attains the same level of the water. Okay, So this, hence we can conclude that potential of A is more. V of A is greater than V of B, container B. Okay, another example we can take. We have also read that two bodies at different temperatures, irrespective of their size and shape, if they are kept in contact. Imagine there is two objects, object A and B, they are kept in contact of two different temperatures. Okay, A is having high temperature, B is having low temperature. Hence, the direction of flow of heat is from A to B, where it is having more heat to B flows. Okay, the temperature, the object it just gives away, A gives away the temperature and B receives the temperature. And so till both the bodies acquire the same temperature, this exchange of heat takes place. Okay, so we can write potential of A here, V of A is greater than V of B. Okay, before moving to the potential difference, let us try to understand the flow of electrons between the conductors. Okay, so here in this diagram or image, you can observe that there is a positively charged conductor and there is an uncharged conductor. When a positively charged conductor is connected or joined by a metallic wire to an uncharged conductor, then the electrons will flow from uncharged conductor to the positively charged conductor. So this is the direction of flow of electrons. Okay, in the next case, when a conductor is negatively charged and there is an uncharged conductor and both are connected by a metal wire, and this time conductor A is of negatively charged. Hence, direction of flow of electron, if you take this is A and B here, the direction of flow of electron is from A to B. In the third case, there is a negatively charged conductor and also the other conductor is of positively charged. There are two conductors and they are joined by metallic wire. This time the direction of flow of electrons will be from negative to positive. Actually, the positive charge does not move. It just appears as if they are moving. Okay, so the conventional current is in the other direction. Hence, to identify the higher potential and lower potential in this case of electric field, when we decide the electrons, flow of electrons direction, and then from there higher potential and lower potential can be decided. So here there is a conductor A which is of positively charged and a conductor of negatively charged, and they both are connected by a metallic wire. This time the electrons will flow from B to A, right? This is the direction of flow of electron. And other hand, the flow of current will be from A to B. So the current flows from A to B. Hence, this conductor, which is conductor A, or the positively charged conductor, has the potential more. V of A is greater than V of B, VB. Okay, so conductor A has more potential or high potential. Conductor B is of low potential. So based on the direction of flow of electrons, we decide flow of current, and this flow of current decides which conductor has more potential. Okay, so when I write the difference of this two, VA minus VB, generally when we write the first one, VA's potential will be more, then the second one, VB, will be less potential. Okay, so potential difference, we can define potential difference as the work done in transferring unit positive charge from one point to the other point through a metallic wire. Okay, here there are two reference points from one point to the other point, or the amount of work done in driving 1 coulomb of electric charge from one point or one conductor to the other point or other conductor against the electric field. Okay, that is known as potential difference. Okay, and it is represented by V is equal to W by Q, and you can observe here in this image a cell is connected through a metallic wire and it is connected to the bulb, and the charge starts flowing from A to B when the current is flowing. Point A, if you take this point, positive end will have high potential, on the other hand negative end will have low potential. So the current flows from high potential to the low potential. As that of the electrons, in case they move from negative to the positive. Okay. So there is a potential difference because each coulomb of charge has a different potential energy at either end of the battery. And so in simple terms, to say that when we have to carry this positive charge from this positive end, here this is a battery, from this positive end to the other end, there need to be a work done. So the energy is spent there. Okay, so V is equal to E by Q, where that E is equal to energy or work. But when we say that energy, work done energy is in driving a unit charge, that is 1 coulomb through a component we call. Okay, so this is potential difference. And SI unit of potential difference is, we know volt it is. And potential difference is a scalar quantity. We can write 1 volt is equal to 1 joule per 1 coulomb. So we can also write like this, 1 volt V is equal to joule per coulomb, coulomb to the power 1. So unit for potential and potential difference is the same. Next we shall move to the concept drift velocity. So as the name itself is indicate, drift means a slow change, we say, okay, velocity. So here microscopically, when we consider a metal or a conductor, it consists of large number of electrons, right? So you know that outermost shell of an atom, if there is an atom here and the nucleus, around the nucleus there will be electrons. So in the outermost shell there will be some free electrons, okay, and these electrons, which are free electrons, move in all the directions and they collide with each other, and they move in a speed in the order of around 10 to the power of 6 meter per second. That is the order of the movement of electron in a metal, free electrons. So during the motion they collide with each other, okay. So their speed and direction of the motion changes randomly at each collision. So if this electron dashes this one and this direction changes, the other electron will move in the other direction and that speed also changes, okay. As a result, all these electrons in a metal, they move in a zigzag path like this, they move in a zigzag path, okay. And when there is no applied field, means you are not giving any external energy, external electric field is applied in this conductor, in this field, then the number of electrons moving in one direction is the same as in the opposite direction. Means imagine this electron is moving here in this direction, so there will be somewhere in this conductor there will be an electron which is moving opposite to this, there will be an electron. And then if this electron is moving in this direction, upward direction, there will be an electron moving in the downward direction. Okay, so for each electron there will be opposite movement of electron. Hence the average drift velocity is 0. Hence there is no current in this case when there is no external electric field is applied in case of a conductor, right? So this is cleared, I think so. Now when the electric field is applied, means you are giving an electric current supply from outside, then what happens? The electrons get accelerated in a direction opposite to the electric field. Means if the current is applied in this direction, electrons will be accelerated opposite to the applied electric field, okay. So how will they move? So each electron will try to, suppose electron has to move now to the right side like this now, because from left to right the electric field is applied, let us take, and this electron, particular electron, has to move like this. From this place it has to move like this straight. This electron has to move straight like this. From this place it has to move like this. This just opposite to this it has to move, and in case of this electron it has to take a diversion like this, it has to move. So this small change here, that is, we call it as drift. They move with little speed, okay. So that velocity, that is called as drift velocity, okay. So from the position, initial position, when the external electric field is applied, then they move to a particular direction to move. So as a result, when the external electric field is applied, the force acts on each free electron in the direction opposite to the electric field, and the electron now, they drift slowly in the direction of the force. Now, as these electrons are slowly moves in the direction opposite to the electric field, in this, the average velocity with which the free electrons are drifted in the direction opposite to the electric field is called as drift velocity. Okay, so now in this diagram you can observe there is a battery here. Let L be the length of the conductor, and when an external electric field is applied, electrons move from negative to positive, and the opposite positive charges are moving from positive to the negative. Okay, so this is the electric field, and now drift velocity we can calculate using this. So how to get the expression for drift velocity now? Let E be the strength of the electric field applied. Okay, and E is the charge of the electron, small e. Then the force on the electron due to electric field, F is equal to E into E. Okay, that is electric field into the charge of an electron. We know that electric field, what is an electric field? The field around the charge conductor is called as electric field, right? So that electric field is nothing but force divided by the charge. Here the electron is the charge we take into consideration. So here E is equal to F by E. Therefore F is equal to E into E, we write. And if M is the mass of an electron, then the acceleration is given by, we know that according to Newton's second law, F is equal to ma, force is equal to mass into acceleration, and make A subject of the formula. So A is equal to F by M. Substitute the value of force here. Force is equal to E, small e, capital E by M. And we know the formula for acceleration. What is acceleration? Acceleration A is equal to velocity by time taken, right? Now if you want velocity, velocity is equal to acceleration into time taken. Okay, so this velocity, if you consider as drift velocity Vd, which is equal to A into time, instead of time taken, we take the time, relaxation time, that is tau here. So since the electron is accelerated for a short interval of time only, so this electrons which are in the particular field, it has to move. So they are accelerated for short interval of time. So that relaxation time we take here as tau. Okay, like this, tau we call it is. Hence substitute the formula value of A here. What is A value? E by M. Therefore Vd is equal to, that is drift velocity is equal to E by M into tau. So this is the expression for drift velocity. So in the exam they may ask for this expression, drift velocity expression. Now how can we define drift velocity? Drift velocity is the average velocity gained by the free electrons of a conductor in the opposite of an external applied electric field. Okay, the expression for drift velocity Vd is equal to E by M into tau, where E is the charge of an electron and capital letter E is an electric field and M is the mass of an electron and tau is the relaxation time. So how do we call this relaxation time? Define the average time that elapses between two successive collisions of an electron with fixed atoms or ions in a conductor is called as relaxation time. So we already noted that before applying to an electric field, each electron will be in their own direction. When the electric field is applied, all starts moving in a particular direction only. Let us take in this direction, this electron has to move. Okay, so by the time they move here from this direction to the particular direction, and they takes a rotation, torque, the tau value, that is torque, they take a rotation. Okay, so and then they collide here. If there isn't any other electron present here, they collide with each other like this. Okay, so all this torque applied, the rotational motion here for this electron, it has to rotate all the way like this, okay, in a particular direction. So this time taken by two successive collisions of an electron with fixed atoms is called as relaxation time. As the temperature increases in the conductor or in a metal, the relaxation time decreases. Okay, when the temperature increases, relaxation time decreases. This point you remember. Let us now check out with the relation between current and drift velocity. Okay, so actually the main relation here, current is directly proportional to the drift velocity. When the current through the conductor increases, drift velocity also increases. So this point you remember. Let us check it out actually how it is. So in a short form, quickly I'll explain now. You just consider a metal wire in form of a cylindrical coil of area of cross section A. So this metal wire, if you cut into piece like this is like a cylindrical form. It takes a form of cylinder, right? Okay, let us take this area of cross section is A and length of the metal wire, this particular length is L, and let Vd be the drift velocity of the electron and E is the electric field, and the time taken by the electron to travel distance L, that is time taken is equal to T is equal to L by Vd, or we can write velocity is equal to distance by time taken. Our distance here it is L is a distance and time taken is T. Okay, and we know that the volume of a conductor, here this is a cylinder, right? Volume of a cylinder we can also write like this, area into h, height of the cylinder. Okay, this full area of the circle, or pi r square h also we can write. In general you can write area into the height. Here height is nothing but the L, right? So we write A into L. So this is the volume. Let N be the number of free electrons per unit volume. Then the number of free electrons in the conductor, if N is the number of conductor, then for the whole conductor, this full volume, N into AL. Okay, that is this point. And if E is the charge of each electron, then the total charge inside the cylinder, that will be Q is equal to N into A into L into E. Okay, so number of electrons. Then we know the quantity of the charge moves through the cross section in time t, that is given by the current. We can write current is equal to I is equal to charge by time, Q by T. So this Q value you can substitute N into A into L into E divided by time, where length by time taken we can write as Vd value we can substitute here, that is drift velocity. Hence we can write I is equal to NAE into drift velocity Vd. So here where N is number of free electrons and A is the area and E is the charge of an electron, and drift velocity if you directly take, therefore you can write I is directly proportional to the drift velocity. Therefore how do we define? This is very important point in the whole derivation. This point, current flowing through a conductor is directly proportional to the drift velocity of free electrons. Okay, so when the current in the circuit is increased, drift velocity also increases. When the current in the conductor is decreased, drift velocity also decreases. Okay, this is the main point to be noted. Next, on moving to a small concept, that is mobility of free electron. Okay, what is mobility? The mobility of free electron is the drift velocity per unit electric field. Okay, that drift velocity what we have taken Vd per unit electric field E. Or you can also define mobility of free electron is the drift velocity acquired per unit applied electric field. Okay, and mobility of electron is represented by like this mu E, mobility of electrons. Okay, or simply you can call it as mobility also. You can write this is the expression to show the drift velocity, mobility of electron Vd divided by E. We can also derive the same from the previous equation, that is we have got an equation for drift velocity, that is Vd is equal to E divided by M into relaxation time tau. So all these factors E, M and relaxation time, all this you can write like this mobility. So E into tau is nothing but mobility into E, that is nothing but drift velocity. And how do we get this equation? Mobility of electron is equal to Vd by E, and we know that the relation between I, current, and the drift velocity Vd, that is I is equal to NAE into Vd. Just now we have learnt. And making Vd as subject of the formula, NAE go to the denominator, therefore VD is equal to INAE. Let us take this as equation number 1. And we have learned that for equation for drift velocity in terms of this electrons, charge, tau relaxation time, and E electric field and mass. So that is VD is equal to E tau E by M. So from this equation, actually this VD you can also write drift velocity like this. VD is equal to E, actually it is of E by M into relaxation time, and you can write the relaxation time here along with this E and take this E separate. Hence we arrive at this equation, and this value of E tau by M is equal to mobility now. Okay, hence we can write drift velocity VD is equal to this full value E tau by M becomes mu mobility into E. Okay, now we want to get only the value of mobility now. So mobility is equal to VD divided by E. So we get this equation. Okay, and also you can equate this to both the left hand sides are equal, and equate the right hand side and substitute the value of this. You will arrive at this equation for mobility. So mobility ME is equal to, you can also write as I divided by NAE into E. Also you can write. Okay, so in the exams there might be questions based on this. Show the relation between mobility of an electron and the relaxation time, or write the expression, or what is mobility, or they can give the mobility and expression, or what is it, definition, and ask you to identify what it is also. And as we look further to mobility, mobility is positive for both positive current and negative current carriers. Okay, although their drift velocities are opposite to each other, for the positive current and negative current, mobility is positive only. Okay, as we check into the dependence of mobility on pressure and temperature, when pressure increases, mobility decreases. So pressure and mobility are inversely proportional. Mobility is inversely proportional to pressure. In case of temperature, when temperature increases, mobility also increases. Hence, temperature and mobility are directly proportional. Okay, moving to the SI unit of mobility, we can get this from this equation only. Mobility is equal to drift velocity by E. SI unit of drift velocity is meter per second. For E electric field, SI unit is volt per meter, right? So when you take this volt to the numerator, it becomes per volt. This is already in the denominator. So when you take this to the numerator, meter, this becomes meter square. Meter square per volt per second is the unit of SI unit of mobility. You can also apply for this equation and check out the other derived units for mobility. Okay, so with this we have completed few important points from the current electricity chapter. In the following videos, I shall continue to take the few more important points along with the numericals, and from the previous question papers also, if selected questions are the multiple choice questions, we will check it out from this basic concepts. Okay, so you can go to the channel playlist. You can check the physics playlist, chemistry, maths, biology, and mental ability playlist also. You will get enough videos which will be useful for your Hstr exam, Gpstr exams. Whenever you are free, you can just watch those videos which will be useful for the exams. Okay, thank you for watching.